Welcome back to the lab. We had a viewer question about if I could go into some detail about what it takes to calibrate a scope. That is a very broad topic, but I will see if I can do it justice. I will get into each piece in detail later in the video, and we'll do some demonstrations on a scope and things like that. So we'll have some stuff fired up, but gonna be a lot of talking, a lot of information, and I hope you guys find it useful. So this is essentially from here up over, including him, including the scope, the meter, maybe an analog scope, but scope, meter. This is what the bare minimum you need to calibrate a Tektronix oscilloscope of the faster series. You do not need to get this elaborate if you're going after a 10 megahertz scope. Actually, there's a piece missing. I didn't move the variac. You also need a variac. So, but all this stuff, all this gear is used in the scope throughout the process. There's some critical pieces of gear. What's on the table here is duplicates. Actually, I have, in my lab, I have the Type 100 series and the 500 series signal sources. I'd love to get the 5000 series scope calibrator, but haven't been able to find one of those yet. But essentially, the three main pieces you're going to need for the signal portions of the scope are high amplitude square wave generator. The 106 will output 108 volt square wave on its main output. You'll also notice that it has a fast rise and fall generator. So that's for tuning the high frequency calibrations up to about 100 megahertz. The fast rise edge on that is only 1 nanosecond. So if you're going to go faster than 100 megahertz, you'll need a faster rising edge. Everything on this table can go up to 350. I can do a 486 with what's on the table. So I'll take the pieces one at a time. We'll go through it, and there's some nuances for each piece of equipment. I'll get into some of them, and hope this helps. We'll start at the beginning. You will need a service manual. So the service manual has all the test points, has all the calibration points. Yes, this is a service manual for a curve tracer, not a scope. This is actually the only paper manual I have, so that's why I'm using it as a stand-in. You can get a lot of these on PDFs. Some of my videos have links to the PDFs for the individual device that I'm working on. Some of them don't. Some of them I've had to purchase from a manual site. But you will need a service manual. The service manual has the calibration, has the alignment procedure, it has the specifications that the scope needs to meet, or curve tracer. It has all the test points in it, it has all the schematics, it has all the switch routing, it has everything you need to be successful in an alignment or a calibration, or even sometimes repair when they get into some squirrely issues. So, absolutely have to have a service manual. As with all troubleshooting procedures, you will need a DMM. Everything starts with the power supply. If the power supply is not good, don't even try to calibrate the scope. It's not going to work. Something's wrong. You have to get the power rails to be in spec before anything else. That's why the very first step in all the manuals is deal with the power supply. If the power supply is not in spec, it's not going to work. You will need a DMM of an appropriate accuracy. For me personally, the 179 is a great meter, but it wasn't accurate enough for me. So my base accuracy in the lab is the 6500, and that's why I use that quite a bit. When I use the high voltage probe, which is right here, you'll typically see me use the Fluke 8840A. The reason for that is the probe matches the meter the best. It sets up a voltage divider with the high voltage probe in the input of the meter. The input of the meter matches the divider on the 20 volt range of the 8840A the best. That's why I use that and not something else. Why I don't use the high voltage probe with the 6500. It would probably work just fine. Measurement will be off a little bit. When you're talking tolerances, when you're measuring 4000 volts, is plus minus 1 or 2 volts really that big a deal? No. Am I picky? Yes. So that's why I typically use the 8840. A Type 106 I use pretty extensively in the calibrations of the scopes, as that's what's called for. This one's been slightly upgraded. I did a video on the modification and the repair of this one. These are GR874 to BNCs. I would have switched these out to BNCs, except the way these fast rise and fall boards are connected in here, it made swapping the connectors really difficult because the boards actually mount to the back of the connector. The one thing to note, and this is actually very confusing in the beginning, and you'll get, I got tripped up by it in the very beginning. The plus transition amplitude is a negative voltage to 0. The negative transition amplitude is a positive voltage to 0. If you're looking for a fast rising edge, you're going from negative voltage to ground. If you're looking for a fast falling edge, you're going from positive voltage to ground. Make sure the polarity is correct because the edges are not symmetric. The falling edge on the fast rise is much slower than the rise, and the rising edge on the fast fall is much slower than the fall. That is also true. So since we're talking about the 106, I'll move up. The newer version of the 106 is the 506. So you'll notice we have the fast rise and fall outputs again. Also remember, fast rise is negative 1 volt to 0. Fast fall is positive 1 volt to 0, and those are on these two ports right here. We have a calibrated amplitude output here, and we have a, depending on where this switch is, we have a calibrated amplitude output on here, or we have a fast or we have a high amplitude output on here where it'll actually output about 100 volt square wave as well. You don't get as much current out of the 506 than you do out of the 106, but that'll be some specifics a little bit later. Period of the waveform is adjustable, and the service manual will call out what this is supposed to be set for. This is a up to 10 volts into 50 ohms, you divide by 2. Over 10 volts into 50 ohms, it doesn't work so well. But there are some checks there where you're checking the 50 ohm inputs on like a 485 that the input resets and protects itself. Standard coax cable on this one, that'll be important later. One of the neat things about this is if you have a scope that you're checking in, if you have one that you know is in cal, if you push this, and then you line up you use this to line up with the graticule on the scope. This will tell you whether it's the scope, what percentage the scope is out, and if it's reading low or high. Now, most 400 series scopes and 7000 series scopes are good within 3%. So, pretty wide tolerance for a scope, but they're not DMMs. They're also a lot faster, where DMMs are pretty slow, but they're more accurate. Moving on to a 184, the time mark generator. This was used a lot for timing before we had very stable clocks. When you start talking about clocks and timing and keeping time digitally and analog and with circuitry, it's not very accurate. Like you got to do a lot to get two clocks to sync up and not drift, especially depending on how long the drift is. It's one of the reasons why we have atomic clocks and everything like that. The basis of my lab in terms of time for when I was calibrating this, it is a GPS disciplined oscillator that goes into the back of my frequency counter as its main 10 megahertz reference. So that allowed me to sync the oscillator up with the satellite GPS satellites, which allowed me to calibrate this very precisely. All the buttons up top, you'll notice the ovens coming on and off. This has an ovenized crystal oscillator in it. If you're going to use this piece of equipment, you have to keep in mind, I leave this off and cold most of the time in the lab. This has a 2-hour warm-up time before it hits its stability spec. So you have to let this thing sit. It's not even on yet. I can turn it on now. Now it's on. But this has to sit and the oven has to warm up for 2 hours before you even use it. Because if your signal sources aren't good, known, and in spec, calibrating a scope with unknown signal sources just gives you an unknown result. That's one of the key things with all of this gear is it all has to be checked, tested, calibrated or aligned if necessary against a main reference. To do all this gear, everything that you see here, you only need a scope, a frequency counter, and a voltmeter. That's it. So you're able to calibrate all of this with that. So the base accuracy in my lab at the moment is the DMM 6500, my 100 megahertz Rigel scope, and my GPS disciplined oscillator for time. That gives me the references I need to adjust the other gear, because the real thing that I'm doing when I'm doing one of these alignments is if I set this to 1 microsecond, 0.1 microsecond periods, am I truly getting 0.1 microseconds out of the output? Or am I getting something different? I have to have confidence in all of this gear that what I set the front panel to is what I'm actually getting. And that's really the big important key is if I tell this I want 0.1 microsecond time marks, I get 0.1 microsecond time marks. If I don't get that, if I got 0.2, I can't calibrate a scope time base to it and then have the scope time base be accurate. So that's the important part. So when you buy all this gear, because all of this came from auction sites and secondhand and things like that, I had to check everything in before I trusted it to use it against calibrated against scopes. So moving on to the modern version of the time mark generator is the 501. Exactly the same thing. It's adjustable from the dial. And then if you push this, you'll get a timing deviation, whether it's high or low or right on target. This and this do the same function. The main difference is the trigger outputs here are slaved to this output. So these will always be the same. There's no way to set them differently. When I'm in the calibration procedure and you see me get that ruler output where it's got the lines every major division, but then it has the minor divisions in there, you can generate 2 different time marks with this. Technically, this can generate 3 different time marks at one time, because I can have 0.1 microsecond markers, 1 microsecond markers, and 10 millisecond trigger outputs, and this is completely happy this will do this. So, but that is something that you can only do with the 184. You can't do it with the 501. Now, where is that normally used? Really in geometry. I don't. And then a couple of the scopes, it calls for that, if I remember correctly, in the delay lines when you're calibrating the delayed sweep. So this is the old way. This is the modern way. These are also tube-based. This is a mix. It has some tubes in it. It has some. It has a lot of solid state in it, but these are a mix. This thing inside is it's built like a Swiss watch. There's a lot of stuff going on in here in terms of getting the frequencies and the timing right. This guy's tube-based as well, and he's tube-based as well. I have a video on these two out. I have not needed to rebuild this yet. This is I did a calibration on it and check it before I had the YouTube channel, and he's been fine. But if anybody's curious as to what he's like inside, I'll pull him open and we can take a look. So, moving over, 191, constant amplitude signal generator. Why he's important is for bandwidth checks and things like that. So, up here at the top, this is the low frequency to high frequency. But one of the reasons why this is so important is at the output here, as I adjust the frequency, I know because it's a constant amplitude sine wave generator or leveled sine wave generator, the amplitude coming out of here is not the same. So when you're doing scopes, as you get to the bandwidth limit, you'll hit the 3 dB down point. I'm cranking this up and I'm watching the waveform shrink. I know I'm getting a constant out of here, but the scope's response is going down, so the waveform's shrinking, and I have to get 3 dB of reduction at the rated bandwidth of the scope. So the way you do a scope with this is you set it up for the reference frequency, which is 50 kilohertz on this one. You'd set 8 divisions of display, and then whatever the rated bandwidth of the scope was, because this goes up to 100 megahertz. So if I was doing a 465, you crank this up to 100, and then you just slowly crank this up, and you'll watch the waveform collapse. As this is going up, the waveform will get smaller. And I'll show this on a scope. I'll bring a scope down and show you guys what this stuff can do. But it just collapses as you crank this up, and as soon as you hit that, I think it's 8 divisions to 5.6 divisions. Once you hit 5.6 divisions, that's your 3 dB down point. You have to make sure the frequency that's indicated here matches the spec of the scope. So if it was a 10 megahertz scope, you'd do this, and then the 3 dB down point would be 10 megahertz. Now, I've got scopes that'll trigger well beyond what they're rated for. I just can't take calibrated amplitude measurements. I can look at waveforms, the scopes will work, I'm not overclocking anything. I just can't take calibrated amplitude measurements after the 3 dB down point because the amplifiers aren't specified, so you know what the measurement really is. So the modern version of the 191 is the SG503. This is the same thing, except the 191 tops out at 100 megahertz. He tops out at 250 megahertz. And move this out of the way. If you got to go faster than that, there's the 504, which tops out at 1.04 gigahertz, I believe. 1.05. So 1.05 gigahertz is where this tops out. This needs a sampling head to go with it. This guy, to be in spec at the output, he needs a special specified cable. There's a special 50 ohm plus minus 0.1% resistance cable, and if you use any other cable with this, it's not, there'll be some losses. It's not 100% specified. If you're doing a bandwidth test and you're using a good quality cable and it's, you know, you're 115 megahertz on a 100 megahertz scope, it's fine. The impedance of the cable, you're well outside the effect of the cable. But all this is it's a high quality coax cable, 50 ohms, where the impedance is an extremely tight tolerance. So you can still find these. These are coming up. These aren't bad. But it even calls out here, calibrated with cable. It's the 0482 cable. So you have to have the 0842. You don't necessarily need to have the -00. The way Tektronix part numbers work is any 0482 cable will work, whether it's a -00, 01, 03, 05. Doesn't matter, that's just a generation of the cable. It's the same part. Same thing's true for tubes, transformers, and other things. If the main numbers are right and the very last two are up or down, should be an okay part for what you're looking for. Maybe not down, definitely up. You could replace a 0-0 with a 0-1 or a 0-5, no problem whatsoever, and everything should be good. So this is the faster one. This guy has a problem. I actually got to get him fixed. His high range isn't working, but his low range tops out at 550 megahertz, so he's good for the 485s, so he's fine. This is one of the specialty cables that you need to calibrate a dual input scope. It's used towards the tail end of the procedure. You can get away with using a BNC T for most things. The critical parameter on this cable is these pigtails are length matched to within 0.1 millimeters. So the cable's not acting like a delay line. So for things like common mode rejection measurements, things like that, where you're looking for 100 megahertz of common mode rejection, incredibly important parameter. Is it a big deal on a 10 megahertz scope? Probably not. Is it a big deal on a 7A13 differential comparator? Absolutely. The cable will act as a delay line, and any length mismatch will cause delay in the signal as it hits the scope. So the rejection modes, it'll show up as signal when it shouldn't be. It's just the noise is delayed a little bit, so it falls out and doesn't cancel itself out. I've been looking for one of these for a while. I did end up coming up with two, so I have what I need now for scopes. So this also is for the phase angle adjustment of the inputs. Checking to make sure the phase angle's in spec on the inputs. So those are really the two places where this cable's the most critical. Another thing is good quality coax. High shield rate, high shield length, things like that. Just good coax cables. Don't use, if you're calibrating a piece of test equipment, don't use crappy connectors and cables. Back in the day when these scopes and this equipment was manufactured, it was at the height of laboratory technology. They were very capable pieces of gear, very expensive to purchase. If you're going to do an alignment on one of these, don't use $3 cables. You don't need to get metrology grade cables. These are actually a Tektronix branded cable. I don't even remember where I came up with these, but a Belden cable, Amphenol, something good quality, not the $3 Amazon cable. Especially nowadays with switch mode power supplies and things like that. There's a lot of noise flying around in the environment. The heavily shielding on the cable is very desirable. Keeps noise off the signals. This is another piece of calibration gear that is kind of hard to come by. When these do crop up, I haven't seen them crop up very often. When these do crop up, especially working, they're very expensive. This is a tunnel diode pulsar. So this is, and if you do end up with one of these, make absolutely sure you do not plug it in backwards. Plugging it in backwards will destroy it and blow up the tunnel diode. So this is where the 106 and the PG 506 differentiate themselves. So not all 506s can drive one of these tunnel diode pulsars. The 106 absolutely can, no problem. There's plenty of current. These sometimes they don't give you enough current to drive one of these. This is for faster rising edges than this can give. So you use these for faster than 100 megahertz. This is okay for 100 megahertz, just barely. Anything faster than 100 megahertz, you need a fast rising edge. The thing with the Bodnar pulsers for doing a calibration is they don't settle. You have a peak that goes up and then they come right back down. You have to actually, it has to come up, settle, and then come down. So you have to, you can't use the Bodnar pulsar for doing the high frequency compensation calibration, because that's what actually this is for the high frequency comp on the vertical amplifiers. The Bodnar pulsar doesn't create a square wave where it settles off, so there's nothing to adjust against. So gotta have a tunnel diode pulsar. You can get close without one. You may not get rated bandwidth, because typically what happens is if everything is working in the scope, everything's running great, no problems, everything works, but the channel's a little low, like it happened to me in the last one, I had to go retouch up the high frequency compensation. So if you're close, if it's a 200 megahertz plug-in and you're off by about 20 megahertz on the 3 dB spec, you probably lost it in the high frequency comp of the amplifier, so you got to speed it up a little bit. And so that's what this is for. This has been verified up to a gigahertz. So obviously I did not do the calibration on this. I don't have anything in the lab yet that can go to a gigahertz. So the person who got this to me was able to validate it for me, so I know it's good. You will notice it is kind of out of date, but it's still good. You will need a scope to fix a scope. It's bad news, but to truly fix a scope, you will need a scope, because for the power supply measurements and a few other measurements and things like that, you will need a secondary scope to do some adjustments, especially if you're talking about doing 7000 series frames. There's a lot you need to scope for. But in a 400 series frame, I haven't done a 400 series in a while, but I need to figure, but I do plan on doing one for the channel here soon. Let me know in the comments if you want to see a 400 series. I've got a 465 and two 485s on the shelf that need going through. At bare minimum, you need to check ripple on the power supply. So you will need a scope for ripple on the power supply. You'll need a scope, and it usually tells you what bandwidth you're going to need in the cal document. The first table in the cal document is everything you're going to need. Probably one of the most critical things you're going to need is tuning tools. Some of the calibration, or some of the cal points and everything like that, require non-inductive tools. This is a typical tuning tool. And then these are actually ceramic. These are 100% non-inductive screwdrivers for doing some of the coils and a few things that you'll find in scopes. You absolutely, and especially a couple of the tuning capacitors, you absolutely have to have non-inductive tools for some of those, because just your hand getting close to the capacitor or the coil will drag the measurement off. So you have to have the tuning tools that are non-inductive. Connectors, terminators, attenuators, and input RC normalizers. Lots of them. I'll go through some of these real quick. These are 50 ohm terminators. A couple of them are from Rigel. This one's a Tektronix Terminator. I only have one Tech Terminator. I got three from Rigel. You typically only need one of these at a time, so 3's a bit overkill. Just note the bandwidth that's on them. These are DC to 1 gigahertz, so I'm good for anything under a gigahertz with these. Not sure what the spec on the Tech one is, but it's the number they call out in all the documentation, so that's good. Those are all good to go there, but you will need 50 ohm terminators, especially on scopes with 1 meg input impedances. RC normalizers. These are for adjusting the capacitance of the primary input so it shows up correctly, and making sure you can compensate the probes and get the appropriate bandwidth out of the scope. These are capacitance dependent, so depending on what scope you're using, and also sometimes depending on what series of scope you're using, you will have to get the 20 picofarad, the 22 picofarad. This is a 47 picofarad. That's for a 47 picofarad. That's for one of the 500 series scopes. I have another 22 picofarad. So I use the 22s and the 20 the most. The 47 I have, but I don't have any 500 series scopes. So you'll need some input normalizers as well. Some general BNCTs and couplers. When you're buying BNCTs and couplers, also make sure everything is 50 ohms, not 75, because most of the calibration documents are talked about in 50 ohm. The 75 ohm is typically in video situations. Everything in scopes is 50, so stick with 50 ohms and everything should be good. But you'll just need a variance of. These are some that came with a couple of my scopes. I have some cheapy ones. So lots of BNC stuff. You will also need probably extenders, a few of just extenders. You will also need some attenuators, 5x, 10x, and I have never been able to find a 2x attenuator. However, I was able to get DC to 2 gigahertz 6 dB attenuators, so 2x attenuators in 50 ohm, so you don't have to get the 10 and the 5. The 2s are easy to find. 5 is not. 10x is not too bad to find. 2x is not too bad to find in modern gear. 5 is not. If anybody knows where I can get some modern 5x attenuators, let me know in the comments. I do want to pick some up. But you'll need 10x, 5x, and 2x attenuators. These are both 50 ohm terminators. They're not the same. This is a 50 ohm series resistor, 2 watts, 50 ohms. This is not a 50 ohm terminator. This is a 50 ohm resistor in line. This is a 50 ohm to ground terminator. So it puts a 50 ohm load on the signal in question. This is what you need, not the series barrel. I made the mistake. I grabbed this really early, and to be perfectly honest, I have never ran into a situation where I actually needed this. So if anybody knows where you'd use a 50 ohm series resistor, let me know, but I have never had to use the 50 ohm series. You need a 50 ohm terminator. They are not the same thing. For an organizer, I just use a toolbox from DeWalt. Actually, it's got nice size bins for the barrel jacks and things like that. These clips break really easy. These clips are pretty stout, so it keeps the lid on, but these clips have popped off. One's busted over here. It's over here, so. But that's what I use for a storage box to keep everything somewhat organized. But let me pull the scope down, get it set up, and then I will show you some of the signals that come out of this stuff. Okay, I got the scope down here, so we will start with we'll just go here. None of this gear is warmed up. So, well, this has been plugged in. This is on and warmed up, but I can turn all this stuff on. Just get it going. Okay, so I've got the Rigel set up to do a preliminary bandwidth kind of verification, I guess. I have 8 divisions of display of a 50 kilohertz signal. So what I can do now is with the 191, this is a 100 megahertz scope, so we should have 100 megahertz. So as you see, as I crank up the frequency, the waveform is growing. In size. So there's 818. There's 18 megahertz. I'm not doing anything but changing the frequency. 42 megahertz. And you can see the waveform shrinking. As I'm adjusting the frequency. And right there we're at, it says 80 odd megahertz. It should be 100. It's probably because it's not warmed up yet. But that's the essence of a bandwidth test. Other than that, it's just validating that the signal is as expected to where it's just using this as validating the signal is expected in the manual. And as that's all this does is output a sine wave. So that's the 191. So we'll turn this on. If I adjust the Rigel correctly, so I have 10 millisecond time markers. We have 10 milliseconds per division on the scope. And all this does is just validating the time base. You should see one marker per division as it goes across, just to make sure the time base is right. Now, since this is bang on, we can adjust the time base of the scope to match this. Using this as a reference, we adjust the scope to refer to this, to the time mark generator. That's how we can get the time, and that's how I can tweak the calibration, the sweep cal, and all the other stuff on the time bases. Now this one, this allows you to do the multiple. Let me lock it in. So this allows you to do major and minor time marks. Zoom in on that. It's kind of hard to see. It allows you to do major and minor time marks. The other function generator, the PG506, doesn't allow you to do that. You have to. That's the main difference between the 506 and the 184. So if I speed this up, let's go to 1 microsecond. Lots of time marks. But if I make the scope 1 microsecond, the crystal oscillator is right where it should be, one peak every major division. 0.1 mic. There we are. One peak, one major division at 100 nano. The amplitude's decreasing as the signal gets faster just because of the limitations on the scope. This is only 100 megahertz. So the 184 will generate out to 2 nanoseconds per division sine waves with the high frequency selector. So it's got ranges all the way up from 5 seconds per division to 2 nanoseconds. But we can do a 5 seconds per division here real quick. Now if I just let the scope run, it should build that out here in a second. And there it goes. And as you can see, we're lining up exactly on the major divisions. Okay, the next instrument we'll hook up is going to be the calibration generator. So what we'll do is we'll undo this. Calibration generator needs not 50 ohms. It wants 1 mega ohm. Speed this up a bit. Play with my trigger. Turn on some averaging to clean up the signal. There we go. So, what the calibrator does is I have it set to 2 volts per division. We have the scope set to 500 millivolts per division. So that's 0.51, 0.52, exactly where it should be. If this was off a little bit, like I was doing a calibration on something, I could pop this out. And that's about 8% high. We can also go down to 8% low. But if I go to 0, it's exactly on the lines where it should be, so the Rigel is exactly in spec for... Okay, and I just noticed something. The bandwidth was falling off way too fast when I was doing the bandwidth check earlier. I don't know if you guys can see it, but there's a little B down here in the corner. I have the scope limited to 20 megahertz bandwidth, so the 3 dB point is 20 megahertz. I'll go back and do that here in a little bit and show you guys what a difference that makes. But that'll get into some scope bandwidth stuff. So that's the scope calibrator. So I can adjust this to 5. We can turn this down to 1. It'll build back out. So at 1 volt per division, we have 1, 2, 3, 4, 5 divisions, exactly as it should. Let's give it 1. That's jumping all over the place. So at 1 volt per division, 200 millivolts, we'd expect 5 divisions. 3 above, 2 below, exactly what we'd expect. So it's just a very precise square wave, and your reference points are the bottom and the top. You just make it the amplitude to be correct. So, the reference for this, and the reason I was able to calibrate it in my lab without a super precise scope, is there's a switch in here that turns off the square wave, and you actually set the level with a DC reference. The DC reference allows you to use the specification of the voltmeter to get the calibration on this unit. So this was checked by the voltmeter for the DC level, and then the square wave was turned on, but the square wave is based off the DC level. So you have a DC reference to do the amplitude calibration. You have in my lab, a GPS reference to do the frequency calibrations to get the gear set, and then go from there. We'll do the, let me get the, we'll use the other frequency calibrator, or we'll use the other leveled sine wave generator to do the frequency measurement. So I can show you guys the bandwidth limit. I was actually starting to think my scope was broke because it was reading very low. Get the right cable, 50 ohm terminator. Okay, so what we're going to do is let's check the... And we'll just set it to a volt. No average, normal mode, measure is off, acquire, or no, hang on. Okay, channel 1, AC coupling. Channel 1 is on. There's the bandwidth limit. Probe is 1x. So what we will do, pull this down, pop that up. Let's get our 8 divisions of display. And we can't even get 8 divisions of display, so we'll back this out to 500. And we'll get our 8 divisions of display. And there we go. Now the neat part about doing a bandwidth limit is you actually don't need to see the waveform. So there's our waveform. It is a full 8 divisions of display. This is supposed to be a 100 megahertz scope, so let's crank it up to 100 megahertz. Well, there's 93. There's 100, and our amplitude is way low. I'll use the scope to measure it so you guys can actually see. So the peak to peak is 1.3 volts, 3.4. That's way low. Should not be that low. Well, now it's 3.76 because I told the scope to go to full speed. So with the bandwidth limit on, it's 1.36. That turns the channel off. Bandwidth limit off, it's 3.76. Clear this measurement so it's easier to see. So well within our 0.5 division spec. Let's actually see how far it'll go. We want 5.6 divisions of okay, we're falling off very quickly. Okay, so the scope is performing incredibly well. We're at 267 megahertz, and let's see. 1, 2, 3, 4, 5. Yeah, we're below. Yeah, right there. So my peak references here is the top edge here. So that'd be 1, 2, 3, 4, 5 divisions, 0.6 to get to this bottom division there. So the scope is, wow, the scope is 100 megahertz. And if I did the math right, its 3 dB point is 257. I will double check that, but I think that's right. That's the way they check a tech scope. So not too bad for the Rigel, 257. See what kind of rise times we get out of it. I'm actually kind of impressed. Because that's at 103 with the bandwidth off, which is still almost... let me make sure my measurement didn't get jacked up. No, that's full. So there's full. There's 103, so that's actually pretty stout for a 100 megahertz digital scope. I guess the bandwidth doesn't measure the same way. Wow. All right, fast edges. Okay. Nothing special. I'm just plugged into the fast rise output and the fast edge is turned on. So he's good to go. I'm just going to crank the amplitude up just a little bit. So we have 2.2 nanoseconds of rise time. The wave generator is supposed to be less than a nanosecond. I'm not sure how the scope is actually calculating the rise time. But that is the fastest time base this scope goes at 5 nanoseconds. So that's pretty steep. Let's average this, see if it'll tighten up a little bit. We'll average it with 32 averages. Nah, it's still running about 2.4, 2.5. So with a rise time, a 10 to 90 rise time of 2.5, it's running, if the math is right, it's running about 140 megahertz, which is very respectable for a 100 megahertz spec. But as you can see, we have this real steep pulse that comes up and then kind of has this lag off and then it fires again. So this is the fall time. So this is not where you want to be calibrating the scopes, because this is not symmetric. This is the specified edge. So the rise and the settle, not the fall and the settle. This is not the specified edge. You can actually see it's leaning a little bit this way. So, but if I flip the output, all I'm going to do is take this out, put this in the fast fall. Now the edges are reversed. We have the slow rise time with the fast fall and the cutoff at the bottom. So you have to be careful which input you use or output you use for the scope. Tunnel diode is going to be way too fast for this scope. The hardest part about calibrating a scope in your own lab is this right here, doing the high frequency vertical compensation with the fast rising edges, especially when you get past 350 megahertz and you start getting into 500 megahertz and gigahertz and stuff like that, especially in the analog stuff. The biggest challenge is the high frequency compensation of the amplifiers, getting that right and getting the scope done. Everything else is pretty easy. And this is also where the expense is to get these fast rising edge. This is not something a function generator can do. This is not something a signal source can do. I have a Tech 284, which is a pulsar. It's 70 picoseconds on this rise time. It doesn't work at the moment. The airline diode, or not, the diode's good. The resistors in the airline have drifted up out of value and the diode's not firing. That's the problem with it. But other than that, it works just fine. But I need to get that fixed and repaired. That might be another video, but I'm even out of my league on that one. I'll be honest. That's a can of worms. But yeah, so that's the fast rising edges and the fast falling edges. So the high amplitude output, I'll just move this over here, kick this over. This is just the high amplitude square wave output. It looks a little funky because I have a 50 ohm Terminator on there. You can get a faster than 12 nanoseconds into 50 ohms, but if I pop this Terminator off, try the other cable here real quick. That didn't look quite right. Maybe because it was fast. I had it set as fast as it would go. Yeah, that looks better. There's a square wave generator. The wave kind of looked a little ugly because I had it going crazy high speed. You typically don't use a 106 at 100 kilohertz. That it's typically used at 1 kilohertz and 10 kilohertz, so we have a nice high amplitude square wave. And if we measure this, let's make it a nice 75. 75 volts a square wave. And let me move over to the 106. Here's where the amplitude is. I've got all this amplitude I could go. So it'll actually do 120 volt square waves. The PG506 is limited at 108, I believe. Yeah, 108. So can get a little bit more square wave, can get a little bit more amplitude out of the 106. I have a video where I repaired that one. I have a video where I repaired the 191, so you guys can see what's in those if you want to. Well, thanks for stopping by the lab and checking out some of the gear that I use to calibrate oscilloscopes and some of the things that's happening behind the scenes as I am working through the process and getting these scopes all tuned up and ready for the bench in the lab so we can use them for future projects and videos. If anybody has any questions, I check the comments below regularly. Feel free to give me a drop me a line. Let me know. If there's anything you'd like to see, let me know, and we'll see what we can make happen. Given the current situation, I am rapidly running out of things to fix in the lab, so I'm going to have to get some more gear here soon. But so if anybody has any questions, let me know. I'll see if I can shed some light on some things. Take care for now, and I'll see you guys in the next video.